We're starting a new chapter today on further differentiation. It will be more challenging than both, in my opinion, than both vectors and matrices. We're going to be extending some of the differentiation that you learned about last semester to look at kind of more complicated curves. And hopefully by the end of this chapter, you'll understand this cartoon. So we'll just do a quick review of some differentiation from Maths 6012, very quick. So the primary thing that you're going to be studying here, that you did study in Maths 6012 is functions of a single real number variable. So these are functions so a function is something, you give it an input, it produces an output. So these functions we're interested in at the moment, you give them a number and they spit out another number. Whereas, say, for example, in chapter 2 in matrices, we kind of described how matrices can be thought about as functions that take in a list of numbers and spit out another list of numbers. In other words, they take in a vector and spit out another vector. But in last semester, certainly when you're talking about differentiation, you're talking about real number in, real number out. So an example is f of x equal to x squared. What this function does is you give it a number as an input and it produces a square of that number as an output. So for example, give it 2, an input of 2 produces an output of 4. An input of 5 produces an output of 25. An input of minus 4 produces an output of plus 16, etc. And what you can do then is, if you want, you can visually represent functions using their graphs. And the graph has infinitely many points on it, all of the form input output. So for example here, let's look at some points. 0 in, 0 out. So you 0 in and 0 squared is the output, same thing. Or we might have 2 in, 2 squared out. Or we might have square root of 7 in, square root of 7 squared, which is 7 out, etc. And you can kind of visualize these things. Now we're going to be interested in functions that are combinations of these functions here. Now at the end of this manual, at the very end, there's a function catalog which might be useful to you next semester that has some properties of these kind of things. Now on the right, I'm just going to kind of roughly draw graphs without axes. So first type is constant functions. Now these are just flat because for every input you have the same output. So if you think about the graph, all the y-coordinates are the same. So they have to be flat. The next thing is a line, which obviously looks like a line. And constants are a line, but with a zero slope. Quadratics either have a U shape or an N shape. And then you can have more general polynomials. So in general, a polynomial, say degree 4, will have 3 turning points. So this one, for example, might look something like that. Powers that are, well, here, this should probably say roots, shouldn't it? Well, I think the fancy word here is surds. But all those things can be written as powers. So square root of x, I'll just give you a rough example, looks something like that. Sine, cos, and tan are obviously, well, sine and cos are waves, and tan is kind of some kind of a messier thing, something like this. You can, of course, look at the function catalog. There should be a graph back there. Inverse sine and inverse tan are the inverse functions of sine and tan. We would have met inverse cos in vectors, so I'll be roughly understand what they look like. Exponential, something like that, gets really, really big, and log looks something like that. It's related to exponential. So these are what we call the elementary functions. And when you're differentiating, you would differentiate these kind of functions, combinations of them. Now, what we mean by combinations is you can do a sum or difference of them. So for example, sine plus a constant function. Scalar multiples, so you can take a surd, cube root of x, and multiply it by 5. Products, so things multiply together. So that's like, what do we got there? X cubed by 10x. Quotients, so that just means one divided by another, essentially. And then compositions. And you can visualize all these things by looking at the graph, and more of this in the back notes. Now, you are kind of expected to be able to differentiate from semester 1. And if you can't, you are in a bit of bother. And you'll probably have to work very hard and possibly use the Academic Learning Center as well. Okay. So how are we going to study these functions? So we developed, or rather you developed, we should say, last semester, the idea of the derivative of a function. And the derivative of a function allows you to study these problems. So let's see. So first of all, a lot of these functions are what are called smooth. Now you can make that a bit more precise, but roughly what it means is if you zoom in, they look like lines. So let's do an example here. Y equal to log of x. So this graph looks something like this. This is the point 1, 0. So near the point x equal to 1, if you zoom in on the curve, now we can't zoom too far here, but it begins to look like a line. And the line it looks like is what we call the tangent. So I'm not great at drawing, I'll do my best here now. That's not bad. Okay, so you can find the equation of this, so it's a line, so you can find the equation of it. So let's write it as y equal to mx plus c. C, by the way, is where it cuts. So here c will have to be negative. And so what are we saying? So smooth basically means that close to, if you zoom in on a point, for example, 1, 0 here, that the graph of log of x looks like the graph of the line. The line that it looks like is what we call the tangent. Okay, now it turns out that this line is x minus 1. Now how is that done? So basically what you do is, okay, you want to find the equation of the tangent line has this equation. We have to find the slope of the tangent. And I won't go over it because it's from last semester, but you would have shown that the slope of the tangent to the graph of a function is the derivative of the function evaluated at that point. So let's do this one quite quickly here. So the slope is the derivative evaluated at x equal to 1. Now you say, what's the derivative of log of x? Well, you go into a tables for that. You get 1 over x, and then evaluate that at x equal to 1. 1 over 1 is equal to 1. So the slope is 1, and we have a point 1, 0. So we do y minus y1. So the y here is 0, is equal to m x minus x1. So we end up with the equation of this tangent line. Y minus 0 is just y, and 1 times x minus 1 is just x minus 1. So that's where we get that equation. So you can use the derivative to kind of look at tangents and stuff. Rates of change. Now, say for example, you have a formula for the temperature of something, and maybe it looks something like this. Okay, for argument's sake. So you have a formula for the temperature at time t. And the question is, suppose you have a formula, can we analyze when it's increasing and decreasing? Can we find the rate of change of the temperature? And it turns out that the rate of change of a function is the derivative, and that's something that you would have done last semester as well. So that's basically saying, it's saying, okay, how fast is the y value, the value of the function, changing when the x value is changing, essentially. And then we can analyze max and min. So for example, and I presume this is something you did last semester, we won't be doing this module, so I'm not too worried about it, but let's see. So how can you find where the local max and the local min? Now the word local means, like if I look at this point here, like it's incorrect to say that that's a maximum, because if you go over here, it's bigger than the max. So this is called the local max. So all it just means is that if you zoom in on it close enough, it's the biggest nearer point. So like the analogy would be, so if you think about, say, the best hurler in the whole country, that would be called the global max, but the best hurler in Cork would be the local max. It's just the best in close to a certain point. So that's the local max, and then we've also got a local min. And usually and often in applications, the local max and the global max coincide. So if you want to find out where these are, well, if you ever climb up a mountain, you go up the top and the mountain is flat. It couldn't be still going up, because then you wouldn't be at the top yet. And it couldn't be going down, because then the top would be behind you. At a peak, it has to be flat. Similarly, the trough has to be flat. Play golf, the bottom of a bunker is flat. So what we have is at both of these points, the first derivative which is the slope of the tangent, is equal to 0. And then you can talk about the second derivative to determine whether it's a local max or min, but we don't need that in this module, so I'm going to glide over it. Okay. Okay. So, no, we are actually, I'm wrong here because it is actually important. Okay, so the second derivative, yeah, it is going to be important. Now, we're not going to find local maximum, but we are going to study something to do the second derivative. Now, take 3 points here. Say, find this point A, this point B, this point C. We'll study that. And then we'll study the point D, E, and F. Okay. Now, what I'm going to do is say, okay, at these points, what is the sign of the derivative? And what I mean by the sign is it positive or negative or 0 or whatever? Okay. Now, if you look, now you need to know from lines that, now we'll just draw, I think, at A anyway, so that will tidy that up. But say at A, if we look at the slope, if it's going up like that, that's a positive slope. So here the slope is bigger than 0. Okay. At B, the slope is equal to 0. And at C, see the way it's going down? It's less than 0. Now, if you kind of run backwards, say if you go from D to C, you'd say, oh, but the slope is going up, but then the x is actually getting smaller. So if you go backwards, if you talk about rise over run or rate of change, yeah, the function is getting bigger, but with respect to a decrease in the x value. So you still get, well, is it positive over negative? Similarly, D, the slope is negative. E, the slope is 0. And F, the slope is positive. Now, so what's going on here with the slope? What's going on here with the slope? So in the first region, so that's around the local maximum, the slope is going from positive to 0 to negative. So imagine your bank balance. You got 100 quid, you got no quid, you got an overdraft of 50 euros. Your balance is decreasing. So in this region, f dashed of x is decreasing. And in the other region, again, think of your bank balance. At D, you got an overdraft, but suddenly the balance is 0. Someone's chucked in 50 quid, and then someone's chucked in another 200 quid. The balance has gone positive. Looking over here at D, E, and F. So D, E, and F, what's happening with F, the derivative? It's gone from negative to 0 to positive. The F dash is increasing. Now we have to talk about rates of change. So the rate of change of some function is the derivative. And what that means is if f dash of x is decreasing, it means its rate of change is negative. So we might just write that up here. For a function to be increasing, the derivative is positive, and decreasing, the derivative is negative. So we've got a region down here where around the max, where the slope is decreasing, and decreasing means that the derivative is negative. And what's the derivative of the derivative? The second derivative. And similar story where the f dash slope is increasing, the second derivative is positive. So what that means is that's something about finding local max and min. But really what I'm interested in, do you see the kind of shape around the local max? It's got that N shape. That's characteristic of a decreasing slope. That's a negative second derivative. We'll do this on the next page again, so don't be too worried. And then look around the local minimum. See that U shape, kind of happy? That is associated with first derivative increasing, so the second derivative is positive. So we'll write all this up above. So basically, so in this region, now how far do you go is a good question. So so when does it change from, so we'll call this region just at the moment sad, because it's a frown. Look, it's a bit sad. It is sad indeed, but it works. And call this region happy. Now, a good question is, when does it change from sad to happy? And actually what you want to do is put yourself here and you're driving a car. Now, I can't draw, but look. So you're driving the car. Look, there's you in the front seat. So look at what's happening in the sad part region. It's the wheel is turning to the right. You see that? Now, you keep turning to the right, locking hard around the whatever the local maximum. Now, there comes a point when the wheel goes from turning right to going straight. Now, where that occurs exactly is probably hard to pinpoint on this picture, but let's say it's here. Now, when you go from turning right, it possibly even happened earlier on. Look, I'm only doing my best. This is called the point of inflection. And it's when, so we've described it in terms of the car, but it goes, it's the point where the slope starts increasing again, or it goes from increasing to decreasing, or decreasing to increasing. So what you have anyway, so at a sad place, and look at this N shape. Now it doesn't have to complete the N, like you can just have that. That's also sad, or that, or that's also sad. That's also sad. So they're all sad. And then happy, you don't have to make a full U. You can just be a bit of U. Something like that. Okay. So this is sad, N-shaped, and this is happy, U-shaped. So we'll call all of these things on the right U-shaped, even if they don't make full U's. And we'll call all the things on the other side N-shapes, even though they don't make N's. And just from the argument on the other side, the graph will be sad exactly when the second derivative is negative. And so like, so the, sad negative, and then happy positive. Okay. And that is something that we will study. Basically, so we're going to have these things where it's actually hard to calculate the second derivative. And all I'm going to ask you is, you're probably going to have you'll have a graph in front of you and say at this point is the second derivative positive or negative. It'll be negative if it's a N-shaped part of the curve, and it'll be positive if it's a U-shaped part of the curve. Okay. Also differential equations, which is going to be very, very important for level 7. You might have touched on it slightly last semester, but we won't be looking at it. Well, we'll see. Actually, we will see it a little bit, but what we'll be doing is show that a function satisfies a differential equation. So it'll be that the function satisfies some relationships between the function and its derivatives. That'll be a good bit later though. So the issue here is that we need to differentiate a function. The derivatives of the functions outlined above, the elementary functions, the sines, the cosines, whatever, they're in the function catalog or tables. I'm going to send you on some tables this week. The question is, how do you differentiate these things? So if you know how to differentiate, say x squared and cos x, how do you differentiate x squared minus cos x? How does that work? How do you differentiate, say you know how to differentiate e to the x, how do you differentiate 6 times e to the x? If you know how to differentiate log and tan, how do you differentiate log by tan? If you know how to differentiate, say, whatever, sine x and square root of x, how do you differentiate sine x divided by square root of x? And what if you know how to differentiate, say, inverse sine and let's say x cubed? How do you then differentiate inverse sine of x cubed, which is what's called a composition? And the answer, well, one thing we should probably say is that this is easy, this is easy. The product rule and the chain rule are a bit harder. Excuse me, the product rule and the quotient rule, and then the chain rule is probably the hardest, which we will look at every time there's an example where you need it. I'll go through it very slowly, but they are supposed to be things that you're able to do from last semester. If they were a struggle, you are going to be in trouble in this chapter. Okay, so they're not really rules, blah 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 blah. So here's all of the different rules. So the one I'll just focus on at the moment is the chain rule, and I'll write it I think I'll always try and write it with this color notation. So your job with the chain rule is to recognize the function as you've got an outside bit and an inside bit. And what the chain rule says, and it's just written just above there, is you differentiate the outside. Then the chain rule says evaluate at the inside. But then the chain rule says you must multiply by the derivative of what's inside. And that's what the chain rule is. Okay. Now, I strongly recommend that you try do these revision exercises. There's some hints there as well. So hopefully you can get a start. So, and the answers are there. Yeah. Okay. So now that that's basic revision. Now we're gonna look forward because we're gonna have to be a bit careful in terms of our language, and we'll do that in the next lecture, I think.